this lecture, we'll find out the area of the green shape. In the drawing, we have quarter circle A or B. It is a quarter circle. Inside this quarter circle, we have line segment AQ that is equal to 5 units. Line segment PQ equals to 3 units. And also, this angle APQ equals to 90 degrees. Our mission is to find out the area of the green shape that is actually a right triangle. So our mission is to find out the area of the right triangle AOQ. The right green triangle AOQ. Okay, so first of all, we focus on the yellow right triangle. PQA, and we will implement the Pythagoras theorem on this yellow right triangle AQP. So actually, according to the Pythagoras theorem, here by PT is the relation from Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse in the right green triangle is AP, and the square of the hypotenuse is AP squared. And it must be equal to the sum of the squares of the perpendicular, that is to say, it must be equal to PQ square plus AQ square. Repeat again. In the yellow right triangle APQ, according to the Pythagoras theorem, we get that AP square equals to PQ square plus AQ square. So AP square equals to PQ square. PQ is 3, therefore PQ square is 3 squared, that is 9, plus AQ. Actually, the hypotenuse in the yellow right triangle APQ is AQ. Therefore, the square of the hypotenuse is AQ square equals to PQ square plus AP square. Repeat again. According to the Pythagoras theorem, in the yellow right triangle, AQ square equals to PQ square plus AP square. AQ equals to 5 units, therefore AQ square is 5 squared, that is 25, and it is equal to PQ square. PQ is 3, therefore PQ square is 3 squared, that is 9, plus AP square. AP square. It again, in the right yellow triangle APQ, 25 equals to 9 plus AP square. We subtract 9 from this equation, and we get that 25 minus 9 is 16. 16 equals to AP square. We take out of this equation and we get that AP equals to 4 units. So actually found out that side AP equals to 4 units. So I write it here. Side AP equals to 4 units. So in the next step, we'll present to you a new rule, and we'll implement the new rule number 2 in our drawing. According to rule number 2, perpendicular from the center of a circle towards any chord, bisect the chord. The center of this circle is located at point O. So from point O, we draw perpendicular on chord BC. So this angle equals to 90 degrees and this angle equals to 90 degrees. We define the touching point of the perpendicular from point O and BC as M. According to rule number 2, the perpendicular OM bisects chord BC. That is to say, BM equals to MC. Yeah, BM equals to MC. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. In this case, from the point O, that is the center of the circle, we draw perpendicular on chord BC. And therefore, according to rule number 2, the perpendicular OM bisects chord BC. That is to say, BM equals to MC. Now we will implement rule number 2 in our drawing. O is the center of the circle. Actually, you can complete the quarter circle to a circle, and therefore, actually, we have here point O, that is the center of the circle. So from point O, we draw perpendicular on AP, on chord AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP as M. So we draw perpendicular from point O towards chord AP. According to rule number 2, the perpendicular OM bisects chord AP. That is to say, PM equals to MA. Repeat again. PM equals to MA. And because of the fact that PA equals to 4 units, it means that 4 over 2 is 2. So PM equals to 2 units, and MA also equals to 2 units. Okay? We define the touching point of the perpendicular from point O and AQ as N. In the next step, we focus on 2 triangles. The right triangle AMN and the right triangle APQ. Okay. Those 2 right triangles. We will prove that those 2 right triangles are similar to each other. First of all, this is the right angle. So angle APQ, this angle equals to this angle that is actually a right angle, the right angle AMN. They are both equal to 90 degrees. But again, angle APQ equals to angle AMN, and they are both equal to 90 degrees, therefore they are equal to each other. In addition, we define angle PAQ as theta. Therefore, angle ANM must be equal to 90 degrees minus theta. And here, in the right angle APQ, this angle AQP must be equal also to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. The sum of the angles in any triangle is equal to 180 degrees. The same thing is true on the right triangle AMN. Okay, so for that reason, this angle equals to 90 degrees. So, in addition, we have angle PAQ that is equal to alpha, and it is actually equals to itself. It is equal to angle MAN. They are both equal to alpha. Actually, this equation, angle PAQ equals to angle MAN equals to, actually it is theta equals to theta. It means that the angle equals to itself. Angle theta equals to itself. Why? Because it is a common angle. Angle theta belongs to the right triangle AMN here, and angle theta also belongs to the right triangle APQ. So it is a common angle. It equals to itself. And finally, well, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to itself. They are equal to each other. Okay? So angle AQP, this angle equals to this angle that is actually angle AMM. They are both equal to 90 degrees minus theta, therefore they are equal to each other. I repeat again. Angle AQP equals to angle AMN equals to 90 degrees minus theta. So actually succeeded to prove that three angles in the small yellow triangle AMN are equal to all the three angles in the big right triangle APQ. Therefore, we actually succeeded to prove that the big right yellow triangle APQ is similar. This is the sign of similar to the right triangle AMN. According to angle similarity rule. That is to say, if three angles in one triangle are equal to three angles in another triangle, then the two triangles are similar to each other. From the fact that the two right triangles are similar to each other, we will conclude that AP in the right yellow triangle over AM in the small right yellow triangle equals to PQ over MN, and it is also equals to AQ in the right big yellow triangle over AN. Repeat again, from the fact that the two right yellow triangles are similar to each other, we conclude that AP over AM equals to PQ over MN equals to AQ over AN. So actually, AP equals to 4 units. Okay? So we substitute AP by 4 over AM is equal to 2. So it is 4 over 2, and it is equal to PQ. PQ equals to 3 units over MN. MN is unknown, so we leave it as it is. And it is equal to AQ, that is 5, according to what is given us in the question, over AM. Okay, is equal to AQ over AN. AN is also unknown, therefore we leave it as it is. So actually found out that 4 over 2 equals to 3 over AN equals to 3 over MN equals to 5 over AN. So 4 over 2 is 2. So 2 equals to 3 over MN. Okay, so here we multiply this equation by MN and we get that 2 times MN equals to 3. We divide this equation by 2 and we get that MN equals to 3 over 2, that is 1.5. MN equals to 1.5 units. I write down in the drawing that MN equals to 1.5 units. From this equation, we can conclude that 4 over 2 equals to 5 over AN. Okay, 4 over 2 equals to 5 over AN. 4 over 2 is 2, so 2 equals to 5 over AN. We will multiply this equation by AN and we will get that 2 times AN equals to 5. We divide this equation by 2 and we will get that AN equals to 5 over 2, that is 2.5 units. We write down that AN, this line segment AN, equals to 2.5 units. Okay. In the next step, we'll focus on here actually we know that any triangle can be blocked by a circle. So we'll focus on triangle APQ and we'll block triangle APQ in a circle. Okay. So here the right triangle APQ. This is the right triangle APQ that I copied from the original drawing. We will block the right triangle APQ in a circle. So, okay. So in this circle, we have peripheral angle APQ that is equal to 90 degrees. Okay. And we have rule number 5. According to rule number 5, any peripheral angle any peripheral angle that is equal to 90 degrees can be blocked. Any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here the diameter of this circle is AC. And we have peripheral angle ABC that is equal to 90 degrees. Therefore, the peripheral angle ABC must rest on the diameter of this circle that is AC. So peripheral angle ABC must rest on AC, that is the diameter of the circle. Okay? So we will implement rule number 5 in our drawing. In our drawing, we have peripheral angle APQ that is equal to 90 degrees. And according to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. So peripheral angle APQ that is equal to 90 degrees rests on chord AQ. Therefore, chord AQ is the diameter of the circle. Okay? Because of the fact the peripheral angle APQ equals to 90 degrees, it must rest on the diameter of the circle. Very simple. Therefore, we see here that peripheral angle APQ rests on chord AQ. Therefore, chord AQ is the diameter of the circle. Chord AQ is the diameter of the circle. That is to say, chord AQ equals to 2r, and r is the radius of the circle. But it is given us the question that chord AQ equals to 5 units. Okay, chord AQ equals to 5 units. So 2r equals to AQ, that is equal to 5. We divide this equation by 2 and we get that r equals to AQ over 2, 5 over 2, that is 2.5. The radius of the circle equals to 2.5 units. Yeah. So And we have already found out that AN equals to 2.5 units. AN equals to 2.5 units. And because of the fact that AN equals to 2.5 units, and the radius of the circle also equals to 2.5 units, it means that the radius of the circle is AN. AN is the radius of the circle that is equal to 2.5 units. And therefore, if the radius of the circle is AN, it means that N is the center of the circle. Okay? If the radius of the circle is AN, N must be the center of the circle. So N point N is the center of the circle. And because of the fact that N is the center of the circle, it means that NQ is also the radius of the circle. Why? Because line segment NQ starts from the center of the circle, that is point N, and ends at point Q, that is the point of the circle itself. Therefore, NQ must be also the radius of the circle, that is equal to 2.5 units. So here we found out that NQ also equals to 2.5 units. It is the radius of the circle. And here, line segment NQ starts from the center of the circle, that is to say from point N, and ends at point O. Here, you can draw here, go and O starts from point N, that is the center of the circle, and ends at point O. This is point O, and also this is point O, that is the point on the circle itself. This is exactly the definition of radius. Therefore, in O it is also the radius of the circle that is equal to 2.5 units. And O also equals to 2.5 units. It is the radius of the circle. Okay, the radius of the circle that we drew here, not the radius of the big circle. In the next step, we will implement the Pythagoras theorem on the right triangle AMO. So this is the right triangle AMO. So this is the right triangle AMO. This is a copy from the original drawing. So here MO equals to 1.5 to 2.5, that is 4. Here MA equals to 2 units. So we implement the Pythagoras theorem on the right triangle AMO. According to the Pythagoras theorem, the right triangle MO, MA square plus MO square equals to AO square. So MA is 2, therefore MA square is 2 squared, that is 4, plus MO square. MO is 4, therefore MO square is 4 squared, that is 16, equals to AO square. So AO square equals to 4 plus 16, that is 20. AO square equals to 20. We take out all of this equation and we get that AO equals to the square root of 20 units. So write it down here. AO equals to the square root of 20 units. So in the next step, we will implement the Pythagoras theorem on the right triangle QMO. We will implement the Pythagoras theorem on the green triangle AQO. That is the triangle that is area we are looking for. Okay, so copy the right triangle the right green triangle AQO. New page. AO equals to the square root of 20 units. The length of AQ equals to 5 units. It is given us the question. So actually, this is the right triangle AQO that according to the original drawing. According to the Pythagoras theorem, we get here that AQ square equals to AO square plus QO square. Okay. AQ equals to 5 units. Therefore AQ square is 5 squared, that is 25. And it is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 squared, that is 20, plus QO square. Here we subtract 20 from this equation. So 25 minus 20 is 5. 5 equals to QO square. We take the root of this equation and we get that QO equals to the square root of 5 units. QO equals to the square root of 5 units. Now it is very easy to find out the area of triangle AOQ. That is the area that we are looking for. That is the area of the green shape. The area of triangle AQO, the squared brackets is the sign for the area. is equal to the base of the triangle. This is the base times the height of the base. AO is the height, but in a right triangle, AO here, it makes 90 degrees with the base. Therefore, AO is the height over 2. So repeat again, the base is square root of 5 units, the height is square root of 20 units over 2. Square root of 5 times square root of 20, it is equal to square root of 100 over 2. The square root of 100 is 10, so it is 10 over 2, that is 5. In conclusion, we found out that the area of the green triangle, the green right triangle AQO, equals to 5 square units. So repeat again, the area of this green triangle AOQ equals to 5 square units. In the next step, I will summarize the lecture. So in this lecture, we found out the area of the green right triangle AOQ. So first of all, we focused on the yellow triangle APQ, and we implemented the Pythagoras theorem in this yellow triangle. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse is AQ, therefore the square of the hypotenuse is AQ squared. It must be equal to the sum of the sides of the perpendiculars. That is to say, it must be equal to PQ squared plus PA squared. Okay, again, in the right yellow triangle APQ, according to the Pythagoras theorem, AQ squared equals to PQ squared plus AP squared. AQ equals to 5 units according to what is given as the equation, therefore AQ squared is 25, and it is equal to PQ squared. PQ is 3, therefore PQ squared is 9, so 25 equals to 9, plus AP squared. AP is the missing 9 segment, so we leave this it is, plus AP squared. Here we subtracted 9 from this equation, and we found out that 25 minus 9 is 16, so 16 equals to AP squared. We took a root out of this equation. We found out finally that AP equals to 4 units. This side AP equals to 4 units. Okay. Then we used a new rule here. According to the new rule, we found that actually we can complete the quarter circle to a circle, and therefore this is actually a circle, and point O is the center of the circle. And according to rule number 2, a perpendicular from the center of the circle towards any chord bisect the chord. Point O is the center of the circle. We have perpendicular from point O is not perpendicular on BC. So this angle equals 90 degrees and this angle equals 90 degrees. We define the tangent point of the perpendicular from point O and BC as M. So this perpendicular OM bisects chord BC. That is to say, it divides it into 2 equal parts, or BM equals to MC. BM equals to MC. We implemented the rule number 2 in our drawing. From point O, we draw perpendicular on AP. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We defined the tangent point of the perpendicular from point O and AP as M. So we have from point O, that is the center of the circle, we draw perpendicular on chord AP. And according to rule number 2, a perpendicular OM bisects chord AP. That is to say, AM equals to MP. Okay, so, and because of the fact that it bisects chord AP into two halves, and AP equals to 4 units, it means that the first half is 2 and the second half is 2. Okay, then we defined this point as N, and we proved that the yellow small right triangle AMN is similar to the yellow big triangle AQP. First of all, we defined this angle as theta, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees, the sum of the angles in any triangle. The same rule is true in the big triangle. In the big triangle AQP, this angle equals to theta, therefore the missing angle must be equal to 90 degrees minus theta because of the same reason. Okay. Then we proved that the big triangle AQP is similar to the small triangle ANM. Why? The two right triangles are similar, the two right yellow triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta is a common angle that belongs to both triangles, therefore the angle equals to itself. And finally, those two angles they are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all three angles in the small right triangle AMN are equal to all three angles in the big yellow triangle AQP. Okay, repeat again. Angle APQ equals to angle AMN equals to 90 degrees, therefore they are equal to each other. Angle PAQ equals to angle AMN equals to theta. The angle equals to itself, it is a common angle. And finally, angle AQP equals to angle ANM. They are both equal to 90 degrees, therefore they are equal to each other. Therefore, the right triangles are similar to each other. This is the sign of similar. From the fact that the right two triangles are similar to each other, we conclude that AP over AM equals to PQ over MN equals to AQ over AN. Okay. AP equals to 4 units, therefore we substitute AP by 4, and AM equals to 2 units, and it is equal to PQ. PQ equals to 5 units, so we substitute PQ by 5 over MN is unknown, so we leave it as it is, and it is equal to AQ, that is 5, over AN, that is unknown. So in conclusion, we found out that (4 over 2) equals to 3 over MN equals to 5 over AN. 4 over 2 is 2, so 2 equals to 3 over MN. We multiplied this equation by MN and we found out that 2 times MN equals to 3. Then we divided this equation by 2 and found out that MN equals to 3 over 2, that is 1.5. From this equation you can also conclude that 4 over 2 equals to 5 over AN. 4 over 2 equals to 5 over AN. 4 over 2 is 2, so 2 equals to 5 over AN. We multiply this equation by N by AN. We found out that 2 times AN equals to 5. We divided this equation by 2, and finally we found out that AN equals to 5 over 2, that is 2.5. So here AN equals to 2.5. And I also found out that MN equals to 1.5. Okay. We have the rule that any triangle can be blocked by a circle. Therefore, we block triangle, the right yellow triangle APQ inside a circle. This is the right triangle APQ. That we blocked inside a circle. This is the right triangle APQ that we blocked inside a circle. And we also have rule number 5. According, we know that the peripheral angle APQ equals to 90 degrees. And we have the rule that any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. This is peripheral angle ABC that is equal to 90 degrees. Therefore, peripheral angle ABC must rest on AC, that is the diameter of the circle. Again, peripheral angle ABQ that is equal to 90 degrees must rest on AC, that is the diameter of the circle. So we implemented rule number 5 in our drawing. We have the peripheral angle APQ that is equal to 90 degrees. Therefore, peripheral angle APQ rests on AQ, that is the diameter of the circle. Therefore, AQ is the diameter of the circle. Read again. AQ is the diameter of the circle. The diameter of any circle equals to 2 times the radius. So AQ, that is the diameter of the circle, equals to 2 times the radius. So 2R equals to AQ, but it is given as the equation that AQ equals to 5. So for this equation, so we divided this equation by 2, and we found out that 2R times 2 is R equals to AQ over 2, that is 5 over 2. R equals to 2.5 units. Here, R, the radius of the circle, equals to 2.5 units. But because of the fact that AN is the diameter, AN equals to 2.5, AN must be the radius of the circle, because AN, and because the radius of the circle equals also to 2.5. Therefore, AN is the radius of the circle, and so AN is the radius of the circle, and so AN is the radius of the circle, and we have here AQ is the diameter, N is the center of the circle. Again, because of the fact that AN is the radius of the circle, N must be the center of the circle, and therefore NQ must be also the radius of the circle. Why? Because it starts from line segment NQ starts from point N, that is the center of the circle, and that's at point Q, that is a point on the circle itself. Therefore, NQ is also the radius of the circle, that is equal to 2.5 units. Okay, and here We have NQ is also, NO is also the radius of the circle. Why? Because it starts from the center of the circle. Line segment NO starts from the center of the circle, that is to say from point A, and it ends at point O, that is the point of the circle itself. Therefore, this is exactly the definition of a radius. So NO is also the radius of the circle, that is equal to 2.5 units. Then we implemented the Pythagoras theorem on the right triangle AMO. I call it the right triangle AMO here. MO equals to 1.5 plus 2.5, that is 4. AM equals to 2 units. So we created here the Pythagoras theorem. According to the Pythagoras theorem, AM square plus MO, AM square plus MO square equals to AO square. AM is 2, therefore AM square is 2 squared, that is 4. OM is 4, therefore OM square is 4 squared, that is 16, equals to AO square. 4 plus 16 is 20, so 20 equals to AO square. We took a root out of this equation and found out that AO equals to square root of 20 units. Yeah. Line segment AO equals to the square root of 20 units. Then we implemented the Pythagoras theorem on the green triangle, the green right triangle AOQ. According to the Pythagoras theorem on the, this is the right green triangle AOQ that I call it from the original drawing. So according to the Pythagoras theorem, AQ square equals to AO square plus QO square. AQ equals to 5, therefore AQ square is 5 squared, that is 25, plus AO square. AO equals to the square root of 20 units, therefore AO square equals to the square root of 20, the square root of 20 square, that is 20, plus OQ square. OQ is the missing side. So here we subtracted 20 from this equation and found out 25 minus 20 is 5, so here we have 5 equals to OQ square. Then we took out of this equation and found out that OQ equals to the square root of 5 units. Here, this side QO equals to the square root of 5 units. Now it is very easy to find out the area of the green right triangle AQO. The area of the triangle equals to the base, that is OQ, times the height of the base, that is AO over 2. The area of the green triangle AQO, that is the area that we are looking for, equals to the base of the triangle times the height over 2. The base equals to the square root of 5 units. The height equals to the square root of 20 units, all divided by 2. Square root of 5 times square root of 20 over 2. Square root of 5 times square root of 20 is square root of 100 over 2. Square root of 100 is 10. 10 over 2 is 5. So finally we found out that the area of this green right triangle, the area that we are looking for, equals to 5 square units. Okay, thank you very much.